Please pause the video and try this problem. And now let's discuss the problem together. Here's a summary of the solution to the problem, and let's discuss the solution step by step. For a circular motion problem, we should draw the object's circular path of motion. Now, the problem tells us that the pilot is moving in a vertical circle. So, we represent the pilot's path of motion with a drawing of a vertical circle. And for the sake of concreteness, let's make the arbitrary assumption that the pilot is moving counterclockwise around the circle. Now, this is the first problem in this video series in which the object is moving in a vertical circle. In the previous problems in this series, the objects were moving in horizontal circles. The problem asks us for the plane's speed at the top of the circle. And the problem tells us to use the symbol v sub t, written without an arrow on top, to represent that speed. This problem is a symbolic problem rather than a numeric problem because the problem gives us symbols to work with, capital R and v sub b, rather than giving us numbers. For a symbolic problem, you should write down a list of the given symbols. A symbol that is explicitly mentioned in the problem is treated as a given. So for this problem, the symbols capital R and v sub b are treated as givens. Now, the symbol v sub t is also explicitly mentioned in the problem, but obviously the symbol v sub t is not treated as a given because v sub t represents what the question is asking us to determine. Usually, a symbol that is not explicitly mentioned in the problem is not treated as a given, but here's an exception. The symbol little g is treated as a given, even though it was not explicitly mentioned in the problem, because little g represents a known physical constant, 9.8 meters per second squared. So we do include the symbol little g on our list of givens. For a symbolic problem, you should always write down the list of given symbols. How will that list be helpful to us? Well, we can treat the given symbols as knowns. So listing the givens will help us to identify which symbols in our equation stand for knowns and which symbols stand for unknowns. Also, only the symbols on our list of givens should be included in our final answer. Based on the concepts that are mentioned in the problem, we can use the Newton's second law problem-solving framework to solve this circular motion problem. We usually apply the Newton's second law equations to the object whose mass is mentioned in the problem, but this problem doesn't mention the concept of mass, so which object should we focus on for this problem? Well, the problem refers to the force exerted by the seat cushion on the pilot. That's a clue that for this problem, we should apply the Newton's second law equations to the pilot, not to the plane. The problem refers to the pilot situation at the bottom of the circle and to the pilot situation at the top of the circle. So, we are going to have to apply the Newton's second law problem-solving framework twice. We will need to apply Newton's second law to the pilot situation at the bottom of the circle. And we will need to apply Newton's second law to the pilot situation at the top of the circle. Which of these two frameworks should we work with first? Well, the problem is asking us to determine the pilot's speed, v sub t, at the top of the circle. That's actually a clue that we need to begin by applying the Newton's second law framework to the bottom of the circle. Then apply the Newton's second law framework to the top of the circle in order to answer the question and determine v sub t. Now, what concept should be our link between the Newton's second law framework at the bottom of the circle and at the top of the circle? Well, the problem tells us that the magnitude of the force exerted by the seat cushion on the pilot will be the same at the top and the bottom of the circle. The force from the seat cushion will be a normal force. So we can use the magnitude of the normal force as our connecting link between the Newton's second law frameworks at the bottom and at the top of the circle. So, here is our plan for solving the problem. The plan is, first, we will use the Newton's second law problem-solving framework for the pilot at the bottom of the circle. to determine n. Then we will substitute our result for n into the Newton's second law framework for the pilot at the top of the circle, and we will use this problem-solving framework to determine v sub t. The plan is we will apply the Newton's second law problem-solving framework to the pilot situation at the bottom of the circle to determine n. We will substitute our result for n into the Newton's second law problem-solving framework applied at the top of the circle, and we will use that framework to determine v sub t. So we're going to begin by applying the Newton's second law framework to the situation at the bottom of the circle. And we begin that process by drawing a free body diagram for the pilot situation at the bottom of the circle. Remember that the problem refers to the force exerted by the seat cushion on the pilot. That's a clue that we should apply the Newton's second law equations to the pilot, not to the plane. So we will draw a free body diagram showing all the forces exerted on the pilot, not on the plane. This free body diagram shows all the forces exerted on the pilot at the bottom of the circle. We should add a dot to our sketch to show that for this part of the solution, we are assuming that the pilot is currently located at the bottom of the circle. We draw a downward vector for the weight force exerted on the pilot. Next, we ask what is touching the pilot. Well, the pilot is being touched by the seat cushion, and we can treat the seat cushion as a surface, which can exert both a normal force and a frictional force. The normal force points perpendicular to and away from the surface that is touching the object. So the normal force exerted by the surface of the seat cushion on the pilot points perpendicular to and away from the surface of the seat cushion. When the pilot is located at the bottom of the circle, the pilot will be sitting on top of the seat. So when the pilot is at the bottom of the circle, the seat will exert an upward normal force on the pilot. We use this symbol, n sub b, to represent the upward normal force in our free body diagram. Notice that we're using the subscript b to indicate that this is the normal force exerted at the bottom of the circle. Now, it's possible that the seat cushion may also be exerting a frictional force on the pilot, but that frictional force will not play any significant role in the solution to the problem, so we can disregard the frictional force. How do we know that it's safe to disregard the possible frictional force in this problem? Well, obviously, one important clue that we can disregard friction for this problem is that the problem never mentions friction. Besides the seat cushion, there is nothing else that is touching the pilot, so there are no other forces that we need to include in our free body diagram. Next, we work on the force table for the pilot's situation at the bottom of the circle. In the first row of the force table, we represent the magnitudes of each of the overall force vectors. We use the special formula W equals mg to represent the magnitude of the overall weight force. We are not given a symbol for the pilot's mass, so we continue to use the symbol m for that mass. Now, for a numeric problem, we would substitute 9.8 meters per second squared for little g, but since this problem is symbolic, let's just continue to use the symbol little g. So in the first row of our force table, we represent the magnitude of the overall weight force as mg. There is no special formula for the magnitude of the normal force, and we are not given a symbol for the magnitude of the normal force, so we will represent the unknown magnitude of the normal force in the first row of our force table with the symbol n, written without an arrow on top. The problem tells us that the magnitude of the normal force will be the same at the top and at the bottom of the circle, so we don't need to continue using a b subscript when we refer to the magnitude of the normal force. Before we break the forces into components, we must choose our axes. We should choose a radial axis that points towards the center of the circle. Now, this dot reminds us that we are currently assuming that the pilot is located at the bottom of the circle. So, we choose a radial axis that points up. Now, in this case, The radial axis is the y-axis. In the previous problems in this series, the radial axis was the x-axis. Label that in this case, the y-axis is radial. We have arbitrarily assumed that the plane is moving counterclockwise around the circle, so we will choose an x-axis that points to the right, since that is the plane's direction of motion at the bottom of the circle. Notice that in this case, the x-axis is tangent to the circle. Now, if you want to, you can also write down a z-axis that points out of the page. The z-axis in this case is perpendicular to the plane of the vertical circle. But the z-axis is usually not important for solving typical circular motion problems, so I will stick with just the x and y axes. We can use this rule to break both of the forces into components. The weight force is pointing down, which is our negative y direction, so W sub y is negative mg. And the normal force is pointing up, which is our positive y direction, so the y component of the normal force is positive n. Include a plus sign in front of positive components because that will help you to remember to include the crucial negative signs in front of negative components. Now we work with the Newton's second law equation for the pilot situation at the bottom of the circle. Our force table includes forces only in the y component, which is the radial component. All the forces are 0 in the x component, which is the tangential component. So, for this problem, we only need to write the Newton's second law equation for the y component. For this problem, we don't need to write down the Newton's second law equation for the x component. For motion in a vertical circle, such as the vertical circle that we're dealing with in this problem, you will typically need to write a Newton's second law equation only for the radial component. In contrast, we saw in the previous videos that for motion in a horizontal circle, you will typically need to write the Newton's second law equation for the radial component and for the component that is perpendicular to the plane of the circle. Now we substitute into the Newton's second law y equation. The problem does not give us a symbol for the pilot's mass, so we continue to use the symbol m for the mass. We use this formula. For this problem, the radial axis is the y-axis. So for this problem, the radial component of the acceleration is the y component of the acceleration. For the pilot's speed at the bottom of the circle, we substitute v sub b, the symbol we were given in the problem. For the radius, we substitute the symbol capital R, another symbol we were given in the problem. The radial component of the acceleration always points towards the center of the circle, and we've chosen a radial axis, the y-axis, that points towards the center of the circle. So, the radial component of the acceleration will be positive. We can substitute this expression in for a sub y in our Newton's second law y equation. Remember that these are the given symbols in this problem. Our Newton's second law y equation contains all three of those given symbols, g, v sub b, and capital R. We can treat those given symbols as knowns. The Newton's second law y equation also contains two unknowns, m and n. We're treating m and n as unknowns because they're not on our list of givens. So should we solve this equation for m, or should we solve this equation for n? Well, remember that our plan was to apply the Newton's second law framework to the pilot at the bottom of the circle to determine n. So we're going to solve this equation for n, not for m. Here's our result from solving for n. Our result for n includes the given symbols, r, v sub b, and g, but the result also includes m, which is an unknown, so we're going to have to hope that the m's will cancel out later in our solution. Notice how our list of given symbols helps us by letting us distinguish the knowns from the unknowns in our equations. Now, according to our plan, next we need to substitute our result for n into the Newton's second law framework as applied to the pilot situation at the top of the circle. Our plan is to use the Newton's second law framework for the top of the circle to determine v sub t, the pilot's speed at the top of the circle. We need to substitute our result for n into the Newton's second law framework applied to the top of the circle. Then we can use the Newton's second law framework at the top of the circle to determine v sub t. We're going to apply Newton's second law to a different point on the circle. So now we need to draw a new free body diagram that applies to the pilot situation at the top of the circle. Now we're drawing a free body diagram showing the forces exerted on the pilot at the top of the circle. Draw a dot at the top of the circle to emphasize that that's the position we're focusing on for this part of the solution. At the top of the circle, the pilot is still being touched only by the seat cushion, which will exert a normal force on the pilot. The normal force points perpendicular to and away from the surface that is touching the object. So for this problem, the normal force points perpendicular to and away from the surface of the seat cushion. The problem tells us that when the plane is at the top of the circle, the pilot is upside down. So the pilot will be located underneath the seat. So when the pilot is at the top of the circle, the seat cushion will exert a downwards normal force on the pilot. We can use the symbol n sub t to represent this downwards normal force. We're using the subscript t to indicate that this is the normal force at the top of the circle. So keep in mind that in this problem, we're using the subscript t to stand for top. In this problem, we're not using t to stand for tangential. Be careful with your free body diagrams. In this problem, at the bottom of the circle, the normal force points up. But at the top of the circle, the normal force points down. You need to memorize this rule. The direction of the normal force exerted by a surface on an object points perpendicular to and away from the surface. Now, the problem says that the force exerted by the seat cushion on the pilot will be the same at the top and bottom of the circle. We know that that force is the normal force. But since n sub t and n sub b point in opposite directions, the normal force is not the same at the top and bottom of the circle. So we can see now that the wording of the problem is a little bit sloppy. What the problem meant to say is that the magnitude of the force exerted by the seat cushion is the same at the top and bottom of the circle. Now we have to make a new force table to represent the situation at the top of the circle. In the first row of the force table, we represent the magnitudes of each of the overall force vectors. The problem tells us that the magnitude of the force exerted by the seat cushion will be the same at the top and the bottom of the circle. We know that that force is the normal force, so we can use the result that we obtained for n sub b to represent n sub t. Here is the result that we obtained earlier for the magnitude of the normal force at the bottom of the circle. And now we can write that same expression in the top row of our new force table to represent the magnitude of the normal force at the top of the circle, mg plus mv sub b squared over capital R. Before we can break the forces into components, we must choose our axes. We should choose a radial axis that points towards rather than away from the center of the circle. And at this point in our solution, we're assuming that the pilot is at the top of the circle. So for this part of our solution, we choose a radial axis that points down. In this case, the radial axis will be the y-axis. Let's also choose an x-axis that points to the left, since that's the pilot's direction of motion at the top of the circle. The x-axis will be the tangential axis. Notice that we are using a different set of axes at the top of the circle than the axes that we used at the bottom of the circle. It is okay to use different axes for different points on the object's path of motion. The important thing is, for each point that you're focusing on in the circle, choose a radial axis that points towards not away from the center of the circle. This is the best approach, I think, for a beginning physics student. We can use this rule to break both of the forces into components. The weight force points down, which is now our positive y direction. So W sub y is now positive. The normal force also points down, which is again our positive y direction. So n sub ty is positive. N sub ty has the same magnitude as the overall normal force, which we're representing with this expression. Include a plus sign in front of positive components. Notice that at the bottom of the circle, W sub y was negative, but because we have changed our axes, at the top of the circle, W sub y is now positive. In order to get the problem right, we need to be careful to get all of the signs right in front of all of our components. Now we're ready to work with the Newton's second law y equation applied to the situation at the top of the circle. Remember that these t subscripts stand for top, not for tangential. We're going to use this formula. In this case, the radial component is the y component, so the radial component of the acceleration at the top of the circle is a sub ty. For the pilot's speed at the top of the circle, the problem told us to use the symbol v sub t. The radial component of the acceleration always points towards the center of the circle. And we've chosen a radial axis, the y-axis, that also points towards the center of the circle. So, the radial component of the acceleration will be positive. We can substitute this expression in for a sub y in our Newton's second law y equation, v sub t squared over capital R. Remember that these are the given symbols in this problem. Our Newton's second law y equation contains all three of those given symbols, capital R, v sub b, and g. We can treat those given symbols as knowns. The Newton's second law y equation also contains two unknowns, m and v sub t. We're treating m and v sub t as unknowns because they're not on our list of givens. Now remember that the question is asking us to determine v sub t, so we're going to solve this equation for v sub t rather than for m. You may already be able to see that fortunately all the m's will cancel out of the equation. On the right side of the equation, v sub t squared is multiplied by the fraction m over r. The most efficient way to remove the m over r fraction from the right side of the equation is to multiply both sides of the equation by the reciprocal, r over m, like this. When we multiply both sides by r over m, not only do the m and the r cancel from the right side of the equation, but the m's also cancel from the left side of the equation. So all the m's have canceled out of the equation. When we multiply the left side of the equation by r over m, we need to write parentheses around the left side of the equation. Then we apply the distributive law to remove those parentheses. If you don't include those parentheses when you multiply by r over m, then you won't distribute the r over m over this second term, and consequently you will get an incorrect result. Now we can answer the question. V sub t equals the square root of v sub b squared plus 2g times capital R. Remember, our answer is required to include only symbols that are included on our list of givens. The symbols capital R, little g, and v sub b are all on our list of givens. So this answer does satisfy this requirement. The symbol m is not on our list of givens, so we cannot include the symbol m in our final answer. So it's a good thing that we were able to cancel all the m's out of our equation. Do our results make sense? The symbol n stands for a magnitude, so let's check that our result for n is positive. All of the symbols in this expression stand for positive values, so yes, our result for n is positive. If our result for n were negative, then we would know that we'd made a mistake. There are some other things we can think about to check whether our results for n and v sub t make sense, but I'm going to save that discussion for the next video. Now let's do a recap of our work on the problem. This is the first problem in this video series which has dealt with motion in a vertical circle, rather than motion in a horizontal circle. On this problem, the radial axis is the y-axis. Compare that with the previous problems in which the radial axis was the x-axis. This is the first problem in this video series for which we had to apply the Newton's second law problem-solving framework separately to two different points along the object's path of motion. That meant that we needed two different free body diagrams, one for the bottom of the circle and one for the top. Notice that the direction of the normal force was different in those two diagrams. Remember that the normal force exerted by a surface on an object points perpendicular to and away from the surface. Similarly, we needed two different force tables and two separate applications of the Newton's second law equation, one for the bottom of the circle and one for the top of the circle. This is the first problem in this series for which it was helpful to choose two different sets of axes for different points along the path of motion. For each point that we're focusing on in the circle, we want to choose a radial axis that points towards rather than away from the center of the circle. So we needed two different sets of axes, one for the bottom of the circle and one for the top of the circle. It is okay to use different axes for different points along the object's path of motion. Based on the axes that we've chosen, at the bottom of the circle, w sub y is negative, but at the top of the circle, w sub y is positive. For a horizontal circle, you will typically need to write a Newton's second law equation for the radial component and for the component that is perpendicular to the plane of the circle. But for a vertical circle, you will typically need to write a Newton's second law equation only for the radial component. So for this problem, which deals with a vertical circle, we only had to write the Newton's second law equation for the y component, which was the radial component for this problem. Be aware that for either horizontal or vertical circles, the tangential component is usually not significant for the solution of typical problems. So, you usually just don't need to worry too much about whether there are any forces in the tangential component. This is the first symbolic problem that we've dealt with in this series. For a symbolic problem, you should write down a list of the given symbols. G is treated as a given, even though it's not explicitly mentioned in the problem, because G stands for a known physical constant. V sub t is not treated as a given, even though it is mentioned in the problem, because V sub t is what the question is asking us for. The given symbols, capital R, V sub b, and G, are treated as the knowns in our equations. The symbols that are not on our list of givens, n, m, and v sub t, are treated as the unknowns in our equations. Only the symbols that are on our list of givens should be included in our final answer. So for example, m is not on our list of givens, so we should not include m in our final answer. Fortunately, all the m's canceled out of our equation. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.